Hello, everyone. My name is Austin Smith, and today we're going to be looking at the exact fitting problem in two dimensions. Suppose you were traveling through a downtown city, aiming to see as much of it as possible. If you listed out the top 60 storefronts you wanted to see, what straight line would you take to see the largest number of attractions? Could you always find such a line? Well, let's look at an example. In this case, I've plotted out 60 storefronts, and in fact, there are 3 lines that each pass through 5 different attractions. Let's view this problem from a different perspective. Just as how calculators often use something called the least squares approach to solve the linear regression problem, what if we instead fit a line using the exact fitting method? In this instance, the best line is the one which intersects with the largest number of points. What is the most efficient method to calculate this line? Well, as it turns out, finding the most efficient algorithm to compute this line is actually an open question in computational geometry. Here, we examine an alternative approach using properties of determinants and simplexes to create a new algorithm implemented in C++. Because this problem has widespread implications, finding an efficient algorithm would have positive impacts on numerous fields, including coding theory, probability, and algebra. So pause here to review this background information. For the rest of the PowerPoint, I'm going to assume that you are familiar with these topics. All right. So let's look at the algorithm. Given a set of n points named S, the first thing we're going to do is go through all n choose 3 combinations of points in S. If these 3 points have a determinant of 0, we know they're collinear, so we add them to the list of possibilities. If not, we discard them. Then for all items on the list, we evaluate their slope and intercept. And then we combine those with the same slope and intercept. Finally, the combined line which intersects the largest number of points is our answer. So now is where we would review some examples. My code is published on GitHub, so for the purposes of brevity, I recommend you either follow the links or the QR code to find it. Let's continue. So for time complexity, by running numerous trials on different sizes of n, we can actually see that a regression analysis shows that a cubic polynomial fits within 0.998 adjusted R-squared value. This is highly indicative that this algorithm runs at O of n cubed time, which is phenomenal. Let's talk about connections to other fields. So one of the most important problems of our generation is how to ensure that we always send correct and uncorrupted data. So here's a cute example about the Curiosity rover. It's an instance in which it was highly important to make sure that we were receiving accurate data. Well, interestingly, error correction codes have a direct correlation with the exact fitting problem. So by finding the largest number of collinear points, we are actually finding the largest amount of errors that can be corrected using a linear code with columns of those points. So as far as future work, I think the next obvious extension is to look at higher dimensional versions of this problem. But beyond that, there's also entirely different ways to approach the problem, such as viewing it from simplicial complexes or even using a commutative algebra approach. Finally, there's some really interesting results regarding the expected value of collinear points, or even the largest number of points in a grid where there is only the trivial solution. This is where we find some connections to probability theory and algebra. These are my acknowledgements. Thank you to all who participated and encouraged me along the way. These are my references. I highly encourage reviewing them. They're phenomenal and extremely, extremely fun. Finally, thank you for listening. I hope you have a great day.